Welcome, my name's Eric. I recently took the MCAT, scored 96 percentile on the Chem Physics section. Lately there's been word going around about being able to score essentially 100th percentile on the Chem Physics section with just knowing the bare essentials and being able to derive all equations. Now, this is partially true, and the example I'm going to give today is actually that of dealing with buoyancy, force due to gravity, and percent submersion. The percent submersion equation that you might be familiar with through memory is the one of following: density of the object over density of the fluid equals volume of the fluid over volume of the object. You might have this memorized. If so, good for you. If not, here's what we can use in terms of derivations. Okay, so the problem that we're presented with is the following. We have the density of water, density of water of 10 to the 3 kilograms per meters cubed. We have the specific gravity of ice, which, when you're talking about specific gravity, all it is, it's a proportional statement about the density of whatever object you're interested in to the density of water. So when we say it's 0.92, we're saying that the density of ice to water as a ratio is 0.92. So what's 92% of this? 920 kilograms per meters cubed. Then we're looking at the specific gravity of seawater, and we're given the value of essentially 1,025 kilograms per meters cubed, and we are asked, what is the percentage of ice above sea? So it's not quite percentage submersion, it's the flip side of that. It's what's not being submerged. And here are possible answers: 5%, 10, 90, 95. Now, right off the bat, I like to draw a drawing, okay? So what do we got? We got the seawater level here, and we're gonna represent the ice roughly as a chunk. Just something like, we'll say like this. Okay? Here's our ice. And what we want to say is the fact that the ice is potentially floating above water, or is at least staying in one position, not accelerating up or down, means that all the forces acting on the object are balancing out. And if we want to make a force-related statement, we say that the sum of forces in the y direction is equal to the force of buoyancy, which is pointing up, right? Minus the force of gravity, which is pointing down. Now, we just said that the block is not going to be experiencing any acceleration, so we can effectively call this zero, rearrange and get the following equation of force due to gravity equals the force due to buoyancy. Now here is where our general understanding of what buoyancy force means, where it becomes very important. And recall, the buoyancy force is essentially the force that is experienced by the block of ice that is the result of the water or the seawater being displaced out by the object. And it really is a kind of a reframing of Newton's second law that says for every action there's an equal opposite in reaction, which I don't think is the best statement, but what it means here is this block is pushing the seawater down, it's exerting a force, and then the water is exerting a normal force back on the block that is equivalent in magnitude, and we just denote that force as being the buoyancy force. So now let's start kind of expanding out each of these. The force due to gravity, we could say, is related to the mass of the object times gravity. And then the buoyancy force, we'll say, is the density of the object times, the fluid, not the object, times the volume of the fluid times gravity, right? Because the density of the fluid times the volume of the fluid is essentially a rearrangement for density equals mass per unit of volume, okay? Now, what we want to do from here is we want to make a relative comparison between that of our density due to the fluid and the density of the object, but we don't have that. So let's do our rearrangement from this, and we're going to say, okay, so instead it's density of the object times the volume of the object times g, we'll put a little O here, equals, again, this right side. We'll just go right side. And then we can use some algebra to simplify it a little bit further. Gravities cancel, and we're left with a nice statement of density of object times the volume equals density of the fluid times its volume. Okay. Now the question becomes, how are we supposed to arrange it? Does density of object go on top, or does the fluid go on top? And here's how you answer that question. You need to ask yourself, what can I say about the volume of the object versus the volume of the fluid in terms of relative magnitudes? So here we're going to look at the drawing. We're going to say the amount of fluid that's displaced in this case, is it going to be less than, equal to, or greater than, or some combination of those things to the object? Okay, so in this case the object is like whatever, we'll call it 100 meters cubed, and then the volume of the fluid has to be less, right? Now if you submerge it a little bit more, still the volume of the fluid displaced is less. The only time when that's not true is if you have full submersion. right? If you have full submersion, then what can we say? They're going to be equal. The volume of the object is equal to the volume of the fluid. So as a statement, what we say is this. Oops. The volume of the object is equal to or greater than that of the fluid. Okay? So from there, now we can come up with an equation for percent submersion. So we're going to ask this. Does it make more sense to say the following? Volume of the object over volume of the fluid, or volume of the fluid over volume of the object? Okay? Now suppose this block represents 100 meters cubed total, and then the fluid here is 75 meters cubed, perhaps. Okay? Sure. Meters cubed. And we can plug the values in. So in the case of the object, we're going to say it's 100 over 75. And as a percentage, this equates roughly to what? I'm not sure. 133%. Right? You can't have 133% submersion. It's just 100% or less. Right? Let's go to the other side. What if we look at this one? It would be akin to 75 over 100, which is roughly 75% submersion. So this is the value that we want to end up using for our ratio. And that's how you derive the final equations. The final equation is going to look something like the following. Density of the object over density of the fluid equals volume of the fluid over volume of the object. Okay? Cool beans. Okay. Then from here, we're going to go a little further. What's the density of the object? We said 920, so 920 over the density of the fluid, which is 1025. And then equals this ratio, which we said, or just made a claim of it being the percentage submersion. So if this is a percent, is roughly 90% submersion, but they're asking the percentage of ice above sea. So if this is submersion, what has to be the percentage above that's not submerged? 10%. So the answer is B. Okay? So for those that are still studying for the MCAT, best of luck. And keep in mind that there are some equations you can definitely derive for the MCAT, but for sure not all of them. Okay, so if you come across a statement on Reddit, which is making rounds in the community, don't feel too discouraged about not knowing all the derivations, because the person doesn't even specify the derivations. But nonetheless, here you go. Good stuff.